Alright, let's go. Number 10. The Tardigrade Vacuum Survival. In 2007, a team of Swedish researchers led by K. Ingemar Jensen at Kristianstad University was studying tardigrades for a much simpler reason. These microscopic animals were known to survive drought on Earth, and the team wanted to measure exactly how tough their dehydration tolerance really was. Standard biology predicted a hard ceiling. No multicellular animal, however tolerant, should survive direct exposure to the vacuum of space, unfiltered solar ultraviolet radiation, and temperatures near absolute zero simultaneously. The combination should shred DNA and boil cellular water within minutes. Then the Photon M3 mission strapped tardigrades to the outside of a spacecraft in low Earth orbit for 10 days. Jensen's team published the results in 2008 in Current Biology. A significant fraction of the tardigrades survived. Not just survived, some resumed reproducing normally within days of rehydration. Scientists proposed the animals entered a fully desiccated state called a ton that halted metabolism entirely, but that alone didn't explain the na-repair speed observed afterward. Later work by Takuma Hashimoto's team at the University of Tokyo in 2016, published in Nature Communications, identified a tardigrade-specific protein called DSUP that physically shields Na from radiation damage, found in essentially no other animal on Earth. If a protein this effective evolved once, in one obscure phylum on this planet, the question becomes whether it needed to evolve here at all, or whether it's simply what survives the trip. Every tardigrade on Earth carries a molecular toolkit built for an environment none of its ancestors ever should have needed to survive. Tardigrades proved biology could survive the trip. The next question was whether biology's building blocks already knew which way to turn. Number 9. The Murchison meteorite chirality bias. In 1997, chemists John Cronin and Sandra Pizzarello at Arizona State University were cataloging amino acids extracted from the Murchison meteorite, a rock that fell in Australia in 1969. A routine inventory task meant to confirm which organic compounds exist beyond Earth. Standard chemistry predicted that any amino acids formed by non-biological processes in space should occur in a 50-50 mixture of left-handed and right-handed molecules, since nothing in ordinary chemistry favors one mirror image form over the other. Cronin and Pizzarello found something else. Several amino acids in the meteorite showed a consistent excess of the left-handed form, up to 15% more left-handed than right-handed, published in Science in 1997. This mattered because every protein in every living thing on Earth is built exclusively from left-handed amino acids. Scientists proposed circularly polarized of-light in star-forming regions could selectively destroy one chiral form over the other, and later observations of polarized light in the Orion Nebula supported the mechanism, but the measured polarization was too weak to account for the full imbalance found in the meteorite. Other explanations involving parity violation and weak nuclear decay were proposed and largely abandoned for the same reason. The effect predicted is orders of magnitude too small. If the molecule that built you was already leaning left before Earth existed, the coin was never fair to begin with. Something in the space between stars may have decided which hand life would use before there was a hand to use it. The molecules were already biased. The next find showed one of them was already sitting in a comet, waiting. Number 8. The Rosetta glycine detection. In 2014, the European Space Agency's Rosetta mission was tasked with something mechanically simple. Get an orbiter close enough to Comet 67P Churyumov-Gerasimenko to sample the cloud of gas and dust boiling off its surface, mostly to understand comet composition for planetary defense modeling. Standard cometary chemistry predicted water, carbon dioxide, and simple hydrocarbons, the expected inventory of a dirty ice ball. Instead, in 2016, physicist Catherine Altweg at the University of Bern published results in Science Advances showing Rosetta's Rosina instrument had detected glycine, the simplest amino acid used in every protein on Earth, streaming directly off the comet's nucleus, alongside phosphorus, a critical ingredient for DNA and cell membranes. Altweg's team measured glycine at concentrations too high to be explained by contamination from the spacecraft itself, and traced its release pattern to dust grains warmed by sunlight rather than the icy surface. Scientists propose the glycine formed through UV photochemistry on ice grains in the solar nebula billions of years before the comet accreted, consistent with laboratory simulations, but unable to explain why phosphorus, a comparatively rare element, was present in ratios similar to those found in living cells. No contamination source has been confirmed. 67P is not unique among comets. It's simply the one we happen to fly next to with the right instrument. The comets crossing the space between stars right now may be carrying the same ingredients past every uninhabited rock in the galaxy. One comet held life's raw ingredients. A single molecular cloud held something structurally more complicated. Number 7. The Sagittarius B2 branched molecule. In 2014, radio astronomer Arnaud Belloche at the Max Planck Institute for Radio Astronomy was scanning the giant molecular cloud Sagittarius B2 near the galactic center, an unremarkable survey task meant to catalog known interstellar molecules using their radio emission signatures. Standard astrochemistry predicted that interstellar molecules should be simple, straight-chain structures. Branched carbon skeletons require more specific formation pathways and were assumed too improbable to form in the near vacuum of a molecular cloud. Belloche's team detected isopropylcyanide, the first branched carbon molecule ever confirmed in interstellar space, and published the results in Science in 2014. The measured abundance implied that branched molecules form in these clouds at rates comparable to their straight-chain equivalents, not as a rare accident, but as a routine chemical outcome. Scientists proposed grain surface reactions on cold dust particles, where atoms slowly assemble more complex molecules over thousands of years. And laboratory recreations of these ice conditions did reproduce simple branching. What they could not reproduce was the efficiency. Real interstellar abundances exceeded laboratory yields by a factor difficult to reconcile with the reaction rates measured on Earth. Amino acids require branched carbon backbones. If molecular clouds routinely build branching structures as a matter of course, the chemical distance between interstellar dust and biology is smaller than the models assumed. Sagittarius B2 alone contains enough of this molecule to fill every ocean on Earth several thousand times over. The chemistry was already assembling itself. What it might assemble into, on a planet that never formed, is a different question entirely. Number 6. The Rogue Planet Habitability Model. In 1999, planetary scientist David Stevenson at Caltech was working on a fairly narrow thermodynamics problem. How much internal heat can a planet retain without a star to warm it? Standard planetary science treated interstellar space as absolutely hostile to life. No starlight, no external heat source, temperatures near 4 Kelvin. Life requires liquid water, and liquid water requires warmth. Stevenson's calculation, published in Nature in 1999, found that a planet roughly Earth mass, ejected from its solar system during formation and drifting alone through the galaxy, could retain enough internally generated heat. From radioactive decay and residual formation energy, combined with a thick hydrogen atmosphere acting as an insulating blanket, to maintain liquid water oceans beneath its surface indefinitely, with no star required at all. Scientists proposed that such rogue planets would be undetectable by every survey method built to find planets, since every planet hunting instrument searches for the gravitational or photometric signature of orbiting a star. Microlensing surveys since 2011, run by teams including Takahiro Sumi at Osaka University, have detected free-floating planetary mass objects at rates suggesting there may be more rogue planets in the galaxy than stars. None have been directly imaged closely enough to confirm or rule out Stevenson's ocean. A planet like this would drift through the dark between star systems for the entire multi-billion-year span of its existence, entirely alone, potentially never crossing a single beam of starlight, and potentially never being empty either. 10 entries in, and every one of them points the same direction, toward the dark, not away from it. Now the numbers get harder to dismiss. Number 5. The interstellar dust grain complexity. In 2006, mathematician Janusz Koss and physicist Nigel Mason at the Open University were modeling something mundane, the surface chemistry of dust grains. the tiny silicate and carbon particles that make up most of the visible matter in molecular clouds. Standard chemistry treated these grains as passive substrates, cold enough that little beyond simple ice formation should occur on their surfaces. Coase and Mason's models and the laboratory experiments that followed showed that UV photochemistry on these ice-coated grains produces amino acids, sugars, and nucleotide precursors directly. In 2023, the Atacama Large Millimeter Array detected methyl cyanide and propene in the disk surrounding a young protostar, confirming this chemistry happens before planets even finish forming. Physicist Fred Hoyle and Chandra Wickramasinghe had proposed as early as 1979 that grain surface reactions could edge toward biology-like complexity, a claim dismissed for decades as fringe. Scientists explaining away the more recent findings pointed to the extreme cold and radiation of interstellar space as hard limits on further complexity. But no one has run the reaction kinetics forward across the 13 billion years molecular clouds have actually existed. Nobody has calculated the ceiling. The dust drifting between every star you can see is not inert. It is doing chemistry, continuously, on a timescale longer than the age of most galaxies, toward an endpoint nobody has finished computing. If dust does chemistry for billions of years, the question stops being whether it's alive and starts being what it's alive as. Number 4. The Oumuamua Propulsion Anomaly. In 2017, astronomers using the Pan-STARRS telescope in Hawaii were doing standard sky survey work, cataloging new objects until they flagged something moving on a trajectory that could only have originated outside the solar system. Standard orbital mechanics predicted Oumuamua's path should be governed entirely by gravity, decelerating and accelerating only as the sun's pull dictated. Instead, astronomers measured a small but statistically significant extra acceleration as the object left the solar system. It was moving faster than gravity alone could explain. Harvard's Avi Loeb and Shmuel Bialy proposed in a peer-reviewed 2018 paper that a thin light sail pushed by sunlight could account for it. Daryl Seligman and Gregory Laughlin countered in 2020 and 2021 with a hydrogen iceberg model, pure frozen hydrogen quietly outgassing. In 2022, Thiem Hong at the Korea Astronomy and Space Science Institute calculated that pure hydrogen ice would evaporate within roughly 10 million years of interstellar travel, far short of the billion-year journey Oumuamua likely made. The hydrogen explanation has a stability problem nobody has solved. What remains true regardless of explanation, the acceleration measured matched, almost exactly, what a light sail would experience, strongest near the sun, absent in deep space, precisely where sunlight would and wouldn't be present. Oumuamua showed no unexplained acceleration in interstellar space. It only showed it near a star. An object built to respond to stars would behave exactly like this. Oumuamua did. Number 3. The dark matter biosphere. In 2015, theoretical physicist Lisa Randall at Harvard was working on a much narrower problem with her colleague Matthew Rees, trying to explain why some dark matter halos appear flattened into disks rather than spherical. A shape anomaly with no obvious cause under standard cold dark matter models. Standard dark matter theory treats the substance as collisionless, interacting with nothing, including itself, except through gravity. Randall and Rees's paper, published in Physical Review Letters, proposed that roughly 5% of all dark matter might interact through its own dark electromagnetic force, cooling, collapsing, and forming structures the way ordinary matter forms stars and galaxies. In 2021, Randall extended the model to propose dark stars, compact objects held together and powered by dark radiation instead of light. A star implies an energy gradient. An energy gradient is the one thermodynamic condition every theory of the origin of life requires. Scientists have proposed no confirmed detection method exists for such structures, since by definition they don't interact electromagnetically with our instruments, which is not a refutation, it's an admission. If dark stars exist, and if dark chemistry can organize the way ordinary chemistry does, a dark biosphere would occupy the exact volume of space our galaxy occupies. Passing through planets, through walls, through bodies, gravitationally present and otherwise undetectable, for the entire 13.8 billion year history of the universe. If something has been sharing this room with you since before Earth existed, the silence isn't evidence it isn't there. Number 2. The plasma life structures. In 2007, physicist Vadim Sitovich at the Russian Academy of Sciences was running molecular dynamics simulations of dusty plasma, charged dust suspended in ionized gas, the kind found in nebulae and planetary rings, for a fairly technical purpose, modeling how such plasmas behave in laboratory fusion research. Standard plasma physics predicted charged particles should repel or attract according to simple electrostatic rules, with no expectation of persistent organized structure. Sitovich's simulations instead produced self-organizing helical structures that rotated, interacted, replicated their own geometry, and could split into daughter structures carrying the same configuration. Published in New Journal of Physics. In 2018, Emma Brady and colleagues at the University of St. Andrews reproduced comparable self-organizing behavior in independent plasma simulations. These structures require no carbon, no water, no biological chemistry whatsoever, only electromagnetic fields and charged dust, conditions present throughout stellar coronae, nebulae, and the interstellar medium itself. Scientists debating whether this qualifies as life have mostly avoided the question rather than answered it. Since the structures satisfy several standard biological criteria, organization, replication, response to environment, while lacking every material substrate biology assumes is required. Whether these structures are alive is a definition problem philosophers haven't resolved. Whether they exist is a physics problem, and the physics says yes, and they may be forming right now in the space between every star in the sky. That leaves the number that started all of it, the one hiding in the improbability of your own existence. Number 1. The cosmic ray panspermia model. In 2018, astrophysicist Tomonori Totani at the University of Tokyo wasn't investigating alien life at all. He was trying to close a much older gap in origin of life chemistry, the sheer improbability of a self-replicating nanomolecule assembling by chance from raw chemistry on a single planet. Standard abiogenesis models require an enormous number of independent chemical trials for even one such molecule to emerge, and Earth alone may not offer enough trials in its entire history to make the odds work. Totani's calculation, published in scientific reports, found that if RNA fragments could survive ejection from one planetary system and capture by another, riding on rock or ice, the effective number of chemical trials across the galaxy's history reaches roughly 10 to the power of 22 planetary systems. Scientists raised the obvious objection first. Could any molecule survive the radiation of interstellar transit lasting thousands to millions of years? Totani's own modeling suggested that RNA embedded even a few meters deep in a modest-sized rock could be shielded enough to survive the trip. No competing model has closed the abiogenesis probability gap without invoking a similarly large number of trials from somewhere. If Totani is right, the space between stars was never sterile. It may be the only reason there was ever enough of a chance for any of this, including you, to happen at all. 10 entries. Different fields, different scientists, different decades. None of them describe an anomaly at the edge of a chart nobody checks. Each one sits inside a routine, well-funded, peer-reviewed research program that was aimed at something else entirely, and stumbled into a result nobody was looking for. The universe is not confused about what it's doing between the stars. We are the ones who assume the space was empty, and every one of these papers found the same quiet argument against that assumption from a different angle. The silence between stars was never proof of nothing. It was just the part of the map nobody had finished drawing yet. If you want to see more videos like this, click the video on screen now.